Hi everyone, this is lesson number 15, originally posted on May 8th, 2020. So what we're going to do is we're going to talk about equilibrium calculations. One thing is that this is originally posted on May 8th. In case you're watching it on that day, I have a review on Zoom and homework number 12 is due, right? On Monday, May 11th is test number 2 on sapling. Go ahead, look at the information on test taking on Blackboard. If you're not watching this, if you're watching this after the test, which I totally understand, reminder that this homework is due on Friday, May 15th. Homework number 14 is due on May 13th. And number 13, lesson number 13, which doesn't have homework, but you should watch it. That's the basis for everything else we're going to be talking about today and through the rest of the week. All right, so let's go through a quick review. Last time we learned about Le Chatelier's principle. Le Chatelier's principle says that if you have a system in equilibrium and you go ahead and you stress it or you cause a change in it, it's going to shift back in order to relieve that stress. Okay. All right. So let's go ahead and review problem 1. Q is greater than K. Which way will the reaction shift? Actually, this is a review of 2 lessons ago. Remember, we said we have a chart here, a number line, where Q can go from 0 all the way up to infinity. Okay, if Q is greater than K, what's going to happen? Well, it's going to shift towards the left. What that means is that I'm going to take some product and I'm going to turn that into reactant. That's what shifting to the left means. All right, the second one is about Le Chatelier's principle. Le Chatelier's principle, for this one, we're told that a reaction is exothermic and temperature is increased. Which way will the equilibrium shift? So it's exothermic. So that means I have reactants going to products. This is a reversible reaction, hence we have 2 arrows. And it's exothermic. That means heat is a product. All right, so if I increase the temperature, that means I'm increasing a product. So that means it's going to shift towards the left. Okay? So what that means is, again, we'd form more reactant. Okay, so that was last lesson. Now let's go on and let's go ahead and do some equilibrium calculations. And we're going to use a process called ICE, I-C-E. We'll explain those later. But for now, let's just look at this reaction. H2 plus I2 goes to form 2HI. All of these are gases, and we're given a K, a big K, not a small k, a big K. That's my equilibrium constant. Equals 50 at 400 degrees C. We don't need this temperature. We just often include it because this would change based on the temperature, but we don't need it. All right, so Q is going to be HI squared over H2 times I2. Products over reactants, and then I raise everything to its stoichiometric coefficient. And K is the exact same thing, but it's now at equilibrium. So one thing I'll be stressing about is we need to be very careful about when we say something is equilibrium. If it's at equilibrium, then we can find K. If it's not, then it's just Q. All right, so K equals 50. So what that means is, seeing that this is products over reactants, if I have a K of 50, that means I have a lot more products than I have reactants. All right, so let's see, and let's think about what happens. If we had 1 molar H2 and 1 molar I2, and I place them in a container. And I want to know what happens. All right, so H2 and I2, these are 2 of my reactants. And looking at these 2 reactants, if I have 1 mole of each of those, Notice I say nothing about HI, so that means there's none, right? This reaction doesn't tell you anything about the amount of aluminum either, so the aluminum, there is none. All right, so I have 0 over 1 times 1. That's 0 squared, not that that matters, but that means that my Q is going to be equal to 0. Okay? Now, Q is equal to 0, so I do a number line. Q is 0, and my K is 50. So what does that mean? I'm going to shift from Q to K. Okay? I always shift from Q to K. So that means I'm going to go ahead and I'm going to shift right. But now the question is, how much do we shift? Let's just go through some stuff and let's try to figure this out. Let's say that we start off with 1 molar H2 and 1 molar I2. And we're told that 0.4 molar H2 and 0.4 molar I2 reacts. Okay? Let's see if this is at equilibrium. Okay, so first, I started off with 1 molar. I said 0.4 molar reacts. So that means I'm going to have 0.6 molar H2. I start off with 1 molar I2, 0.4 molar reacted. So I have 0.6 molar I2. Okay? And now, those are my H2 and I2. Now remember the conservation of mass. What that means is I don't just lose H2 and I2, I need to form HI. So if I have 0.4 molar of my H2 reacting, how much H2I do I form? I'm going to form 0.8 molar HI. Okay? This is stoichiometry. Okay? I can say that for every 1 molar of H2, I form 2 molar of this. All right, so now let's go ahead and plug these in for my Q. And I'm going to have to erase some stuff. So I plug them in, and I get a Q of 1.8. You can do this on your calculator. Make sure you include what's on top and what's on bottom, and be very careful about that. All right, so Q is 1.8. So that means Q is 1.8, K is 150. So what's going to happen? I'm going to shift from Q to K. And so it needs to shift more to the right. Okay? If Q is equal to K, I'd be at equilibrium, but I'm not. Okay? Q is not equal to K. Now, what's going to happen? I'm going to shift to the right, but notice this is a reversible reaction, so some's going to go to the left, but not enough. Right? So more is going to the right to form products. A little is going back to reactants, but most of it's going to the right. Okay. So we started off with Q equals 0. We shifted some. We got 1.8 for Q. Now let's try some more. Okay. Let's say we add 0.8 molar H2 reacting. I started off with 1 molar. By the way, all I'm doing is I'm just making up numbers right now, okay? I'm saying, let's say 0.8. In a little bit, we'll actually figure this out. Okay, so if I add 0.8 molar, that means I would be left with 0.2 molar H2. I'd also have 0.2 molar I2. And oops, that I looks horrible. And if I went ahead and I had 0.8 molar of I2 reacting, that's going to form 1.6 molar HI. All right, let's go ahead and plug these in for my Q. And what do I get? I put my products on the top. That's my HI. I put my reactants on the bottom. And I end up with a Q of now 64. Notice in this case that Q is larger than K. Okay? Q is bigger than K. So what's going to happen? It's going to have to shift towards the left, right? And so this has gone past equilibrium. Okay, so we still haven't found equilibrium. Let's just do one more. And again, I'm making up a number. I'm going to say, let's say it's 0.78 molar H2 reacting and 0.78 molar I2 reacting. Okay? Well, in this case, I'm going to get, for my H2, I'm going to have 0.22 molar left over. For my I2, I'm going to have that much left over. And for my HI, I'm going to end up with 1.56 molar formed. I plug these in for my Q, and I end up with a Q of 50.0. So Q equals K. I am at equilibrium. Okay? Now, what does this mean? Well, this means if I ever have an equilibrium calculation, I could just go ahead and I could guess numbers until eventually I get to Q equals K. But that's going to be a pain, right? We're going to go through a way to actually calculate this change. Okay, let's just review this, right? We started off with Q equals 0. We had some of that converting into HI. We got Q equals 1.8. Then we did some more and we got Q equals 64, and that was too far. So what had to happen? It actually shifted back towards the left until Q equals K. Okay? How do we do this? What we're going to do is we're going to use the ICE method. The ICE method says I'm going to look at my initial concentrations, then I'm going to figure out the changes in those concentrations, and then finally I'm going to calculate the equilibrium concentrations, ICE. Okay? And this is going to allow me to figure out my equilibrium concentration. All right? So typically what happens is we're given initial concentrations, we determine changes in concentration, and then finally we calculate equilibrium. We're going to build up to do an ICE calculation, and then you're going to do one. And then next time we're actually going to do some harder. All right, let's go ahead and let's just do some refresher stuff. This is stuff from 215. I was originally going to do it on the screen, but I need to get up, do it on the board. It's actually late at night. Who knows? You don't know what time of day it is or anything, because this could be anything. But it is late at night, so I need to get up, get some energy. All right. So number one, let's say we have 2.8 molar or 2.8 moles of NaCl, and we put this. Remember, NaCl, that's salt, table salt, and we dissolve this into 700 mLs of water, okay? And we want to know its molarity. Well, what is molarity? Molarity is moles per liter. We've done this enough this quarter, so we probably know this. Moles over liter, so I can put this. I can convert from 700 mLs. By this point, I can do this in my head. I get 0.7 liters, okay? If you're still getting 700,000 liters, look at this, study this, find this online, come to office hours, come to SI. Let's get this done because you need to figure this out. Okay? And this is going to give me 4.0 molar or 4.0 moles per liter. Okay? That is my molarity. All right, let's move on to the second one. Okay, in the second one, I have erasers somewhere. They're right here. All right. In the second one, now we're looking at some math problems. Okay. We're taking 5.00 minus 2 times 10 to the minus 6. Okay. And I want to calculate this to, it says 3 sig figs. Okay, I probably should have given you 2.00 times 10 to the negative 6 to actually do it. But I want to have this to 3 sig figs. So when I do this in my calculator, this is what I get. 4.9999998. Right? I don't know if I said the right number of 9, so I'm just going to write it down. I end up with 59. Right? That's my answer. Okay. How many sig figs does this have? 3, 6, 7. So I need to round to 3. So I'm going to keep these, and this is a 9, so I'm going to round up to 5.00. Okay. Wait, I started with 5. I did some math, and I ended with 5. That happens sometimes. If I take a number and I subtract off a really, really small number in comparison, I may end up with that original number. Okay? That change is so small, it has no effect. Okay? The third one thing we're going to talk about, third and fourth, we're actually going to do some stoichiometry. So let's say we have that reaction at the top, N2 plus 3 H2 goes to form 2 NH3. And what are we told? We're told 3 moles N2 reacts. Okay, how much NH3 forms? Well, I can say for every 1 mole N2, I get 2 moles NH3. That gives me 6 moles NH3. Easy peasy. Right? All right, let's go ahead. Oh, by the way, notice how I used this. I said delta NH3. Right? The change in the NH3 concentration. All right, second, we're told that 6 moles N2 reacts. And we want to know how much NH3. I can just do the same thing, 2 over 1. And here, I'm going to get 12 moles NH3. All right. So I doubled the amount of N2. I doubled the amount of NH3. Okay, so this is just a little bit of a refresher, because now we're going to go and we're going to do those actual ice tables. All right. Before we do that, let's look a little bit about at the C in ice. That means changes. Changes. All right. So we're going to look at relative concentration changes. So let's say we have 1 liter and we have 2 moles NH3. So my delta NH3 is plus 2 molar. Okay. Now, if my products increase, what does that mean? My products need to come from somewhere. So my reactants have to decrease, right? If I want to go ahead and go to my kitchen over that way, that's why I point that way whenever I talk about kitchen. If I want to go to my kitchen, actually, I'm not going to show my face probably for this. So anyway, I go to the kitchen, I make some cookies. I'm going to increase the amount of cookies, but I'm going to decrease the amount of flour I have in my kitchen, right? That's what happens. So if I increase my amount of product, my reactants are going to decrease, okay? And if it's plus 2 molar for the NH3, it's going to be minus 1 molar for the N2 and minus 3 molar for my H2. These are my relative changes, okay? This is all based on stoichiometry like we just did. Let's look at scenario 2. Scenario 2 is I have twice as much. So in scenario 2, if I have 2 molar NH3 and that becomes 4 molar NH3, then I go from -1 to -2. And I go from -3 to -6. In the same way, I use two cups of flour to make 1 batch of cookies. If I make 2 batches of cookies, it's going to be 4 cups of flour, right? And so I can generalize this and say, based on the stoichiometry, whatever X is, X can be any number, okay? If my NH3 is plus 2X, my N2 will be minus X, and my H2 would be minus 3X. I'm looking at that stoichiometry, right? And I'm just saying, hey, if these are minus, this is going to be plus, and I'm looking at these coefficients, okay? For every times this increased by 2, this is going to go down by 1, okay? These are relative changes. They're based on stoichiometry, and you always see opposite signs for reactants and products. Okay? This is key, and I want you to go ahead and do video problem 15A, right? So in A, we're looking and we're told I2 plus I minus goes to I3 minus, and we're told minus X for the I2. What are the rest? Here I'm told plus X for the C2H2. What are the rest? And then here in C, I'm not told what are positive and minus, so I can say it either way. I could make this negative, or I could make this negative. If I make this negative, it'd be minus 3x, and therefore these would be positive. Meanwhile, if I make this over here negative, then this side will be positive. Okay? But go ahead, look at that, try to figure it out, and watch that video, because it's going to be really important. Okay, so next, so we talked about C, the changes in concentration. Next, we're going to talk about ice tables. Okay, ice tables are a series of steps we're going to use in order to do ice calculation. Okay, so they're also called ice chart, depending on where you see it. All right, so let's go ahead and look at a problem. Let's say we are told that we have I2 plus I minus goes to I3 minus. Okay, everything's aqueous. So what does that mean? All of them are in my Q and my calculation for K. Okay? And we're told a solution has I2 equal to I minus equal to 8 molar and no I3 before reaction. Before reaction means that these are going to be my I, my initial concentration. At equilibrium, 99% of the I2 has decomposed. So this will go ahead and I'll use this to find my equilibrium. And so I want to know what is my K. All right, before we do this, let's just understand what that means. It says 99% of the I2 has decomposed. Well, let's think about this. If I started with $100 and 99% of that money has decomposed to Target or wherever, that means I'm left with $1, right? So if 99% decomposes, what that means is I'm left with 1%. Okay, so 1% of 8 would be 0.08. All right, so what we're going to do is we're going to fill out an ice chart. Okay, ice charts, we put the reactants or the reaction at the top. So I have I2 plus I minus going to I3 minus. I go ahead and a lot of times when I draw this out, I like to make sure I differentiate between reactants and products. Okay, I go ahead and I put ICE, initial change in equilibrium. Okay. By the way, sometimes they call these Rice tables because you put the reaction at the top. I think that's just stupid. It's called the nice table, so we just use that. All right. So now what we do is we write in the information we know. We know that we start off with 8 molar of the I2 and the I minus. We were told this was before reaction or initial. We're told that we had no I3 minus at the beginning. so 0. Okay. We have here, based on the last, that 0.08 molar is at the end. Okay. So this is the ice chart. We start off with what we know. Okay. By the way, in ice charts, we always use molarity. Okay. At least through this part. Eventually, we're going to use moles. We can use moles or molarity, but for right now, we are going to use molarity. Okay. All right. So I start off with my initial. Now I'm going to go ahead and I'm going to plug those in to my equation for Q. Right? My equation for Q is going to be I3 minus product over I2 times I minus. Okay? I plug in these values, I get 0. Okay? If I have something where I have no product, what that means is my Q is going to be 0. Okay? All right. Next, so I start off with my initial. I found Q. Now I compare Q and I say, well, how do I get from Q? Okay? Well, now, notice what happens. I go from 8 molar I2 to 0.08. So what has to happen? I need to lose. Right? So I'm losing I2. So I can say this is negative x. My I minus will also be minus x. And my I3 minus will be positive x. If my reactants are minus, my products have to be positive. Okay? And notice that these are all 1, 1, and 1. So all these are negative 1x, and positive 1x. If instead this had been 3i3 minus, this would be plus 3x. All right, so, but that's not the case, so let's get rid of that. All right, so let's review. I start off with my initial. I figured out my Q. I realized that I'm going to shift towards the right. So then I plug things in for my C. And now what do I do? Now I go ahead and I say, well, at equilibrium, I'm going to have 8 minus x. Here I'm going to have 0 plus x. Why? Because if this is my initial and this is my change, this is what I'm going to have at equilibrium. Remember, if I start off with $0 and my change, the amount of money I get is 50, I'm going to end up with 50. 0 plus 50. All right. So what is x? Right? Well, this one is also 8 minus x. But we know that 8 minus x is equal to 0.08. So that means that if 8 minus x is 0.08, that means that x must be 7.92. Okay? Oops, this is wrong. All right. So that means that my answer, x, must be 7.92. All right, so now that I know that x is equal to 7.92, 8 minus x will give me 0.08, and 0 plus x is going to give me 7.92. Okay? Now what can I do? Well, now I can go ahead and I can plug these in for my k. Because my k is going to be I3 minus, that's 7.92, over 0.08 times 0.08. All right? And that's going to get me a k of 1238. Okay? All right, so what did I do? Right? I used my information to go from I to C to E. Right? this is an ice chart problem, okay? So I start with my reaction. I put, so my reaction's up here. I put initial change equilibrium. I use my initial values to find Q. Then based on Q, I can figure out my changes. Then I go to equilibrium. All right, so we just did a problem where we used an ice chart to calculate K. Okay? That's usually not what we're going to do. Usually, we're going to use ice charts to figure out equilibrium concentration. I call that equilibrium delta, or X concentration, X in brackets. Okay? All right. Ice charts are hard. Okay? You will not be able to get it the first time. Okay? If it were easy, I would tell you it'd be easy. And when you came to me for questions, I'd say, what? That's easy. It's okay to struggle. Okay? Come to office hours. Come to SI. I'm going to give you some resources outside. Try it. Figure it out. Struggle, and you'll get through it. Okay. All right, so we're going to do ice problems. We're going to start off with some simple ones. Then we're going to do hard ones. And then we're going to do some other varieties. Okay. So, let's do a problem. We have H2S gas going to form 2H2 gas plus S2 gas. And we have a K of 2.2 times 10 to the minus 6. What are the equilibrium concentrations if H2S is 0.824 molar initially? All right, so we're going to use this ice chart. I'm going to put my reaction on top, then ICE. But let's do it on the board. Okay, so we're going to do this problem. 2H2S gas goes to form 2H2 gas plus S2 gas. We're given a K, and we're asked for the equilibrium concentrations. Now, this is the second time I've done this problem, and I'll show you where I messed up, or how I knew that I messed up. Okay, these are tough problems. You need to give yourself a lot of space on the page. Make sure you go step by step, right, to figure it out. Okay, so what are we told? We're told we have 0.824 molar of my H2S initially. Notice I say nothing about H2 and S2 initially. So what can I do? I can just say these are 0. Okay? All right, let's make a little better use of this. Okay. So I go ahead and I start with my initial. Then what I do is I go and I plug those in for Q. Remember, Q is going to be H2 squared times S2 over H2S squared. That's going to give me 0, right? Because it'll be 0 squared times 0 over this. As soon as I know these are 0, it's 0. All right, so my Q is 0. My K is 2.2 times 10 to the minus 6. This is bigger, so it's going to shift towards the right. Okay? All right, so I start off with initial, then I calculated Q, then I use Q in comparison to K to figure out the shift, right? I'm kind of doing a snake pattern. Now I'm going to use that shift to answer these, okay? So if I'm shifting towards the right, that means I'm increasing these, and I'm decreasing this. Then I go ahead and I say, this will just be plus x, this will be plus 2x, this will be minus 2x, okay? That's based on the stoichiometry. So at equilibrium, I'm going to have 0.824 minus 2x I'm going to have 0 plus 2x, or just 2x. And I'm going to have 0 plus x here, or just x. Okay? Now I go ahead and I plug those back into this But now, seeing that I'm at equilibrium, this is no longer Q, this is now K. So I start here with my initial. I go like this to find Q, then I figure out the shift, then back here, then I figure out equilibrium, and then back. And this doesn't really help, and it is gone. All right, so I plug those back in. So K equals 2x squared times x over 0.824 minus 2x squared. Okay? And this is going to equal 2.2 times 10 to the minus 6. Okay? So I have this, and now I'm going to use this to find my x. So 2x squared will give me 4x squared times x is going to get me 4x cubed over 0.824 minus 2x squared equals 2.2 times 10 to the minus 6. All right, so now at this point, I need to realize that this would be really tough to find x. Okay? In fact, we need to use some complicated math to find x because I'll have an x cubed term and I'll have an x squared term. It'll be difficult. Okay? And so, but notice at the top there it says it's simple. So what we're going to do is we're going to use an assumption. Notice this. Q0 and K is 2.2 times 10 to the minus 6. Those are both small numbers. To go from Q equals 0 to K equals 2.2 times 10 to the 6, that means that shift is very small, or X is small. And so if X is small, I can go ahead and make an assumption. Okay? Before I do that, I'm just going to clear myself some space. Right? You can just grab another sheet of paper. I need to erase some stuff or start drawing on the walls, but I'll just go ahead and erase. So those are my equilibrium. I went ahead, I got this. 4x cubed over 0.824 minus 2x squared equals 2.2 times 10 to the minus 6. Right. By the way, notice how I had a 2 here, so I get a 2 here, and I get a 2 here, right? A lot of times, if I have a 2 in the stoichiometer or in the coefficient, I get repetition. I get 2, 2, 2, right? So always be looking for that. All right, so I'm going to assume x is small. What does that mean? In a little bit, we'll explain when we can assume it's small, but for now, we'll just assume it's small. So if x is small, then 0.824 minus 2x, I can just assume that that is 0.824, right? I'm just saying x is so small that subtracting it from this isn't going to have an effect. So it's just 0.824. So this makes my life much simpler, because then this becomes 4x cubed equals 0.8 over 0.824 squared equals 2.2 times 10 to the minus 6. I can go ahead, I can rearrange this, I can find this value. This will be 4x cubed over 0.679 equals 2.2 times 10 to the minus 6. I can rearrange this, get 4x cubed equals that, or x cubed equals, I told you to clear up some space, so I'm going to do it too. 3.73 times 10 to the minus 7th. Okay, now what I need to do is, notice this is x cubed. So I need to do the cube root of this. Right? So the cube root, to do that, I go ahead and notice on my calculator I have x square root y. So I have my number there. I go second, this, and then cube. And I get my answer, which is 7.2 times 10 to the minus 3. Okay? All right. So that's my value for x. Now, here's the thing. Just like Indiana Jones said, x is never the answer, right? X is just a stepping stone to figure out those equilibrium concentrations, right? So I plug that back in, okay? And I go ahead and I can say my equilibrium, 0.824 minus 2 times that number. And that's going to get me all right. Notice my k has 2 sig figs, so I'm going to have all my answers here with 2 sig figs. So it'll be 2 times 7.2 times 10 to the minus 3 for H2. And then this is just x, so that's easy. Okay, so these are my answers. Okay. My amount of H2, my amount of H2S, my amount of H2, my amount of S2. Okay. Now, I have to do 2 things. The first is that I need to check my work. And I need to check my work because I make mistakes. And I say I as in this guy right here, okay? I made a mistake earlier and I caught it by doing this step, right? I go ahead and I say, well, these are my equilibrium concentrations. So why don't I plug those back in and I see if I get this K, right? So I'm going to say that K equals this squared times this number over this number squared. Okay, why are they squared? Because at the very beginning I said they're squared for Q and for K. All right, I go ahead, I plug this all in. I'm not gonna do it step by step because you can do that later. But what do I end up with? I end up with 2.15 times 10 to the minus 6 for my answer. Okay, I start off with 2.2 times 10 to the minus 6. This is it. So I'm really close, right? Why am I not exact? Because I did have to do an assumption. Okay, so I can say, all right, I did it right. Okay, now I'll go ahead and I'll show probably, hey, where I messed up on that previous time, and I'll say, that guy's an idiot, but we make mistakes. All right. And that's going to get me not the right answer. Let's look at this. So what did I get? Sorry, let's just That gets me this number, 9.1 times 10 to the minus 6. Notice I started off with 2.2 times 10 to the negative 6. I ended up with that, so I did something wrong. This is a good example, right? I did something wrong. So now I can go ahead and I can just check and make sure, okay, did I make that mistake here or is it further up? Okay, so let's go through this on the screen, okay? And then we're going to come back to the fact that we need to check this assumption. Okay, so we start off with our initial concentrations, what we're given. We use these to calculate K. Once we know K, we use those to find Q. Once we find Q, we can see that Q is less than K, so it shifts towards the right. So that means these are going to be positive, these are going to be positive. My reactant is negative. Then I go ahead and I plug those in to get my equilibrium concentrations in terms of X, and then I plug those back in, okay? Let me just go and highlight the path I use. I start off with initial. I use those to find Q. Then I find the shift. Then I find the changes. Then I find equilibrium. Then I plug them into K. Right? I go ahead. I get this value. And then I go ahead and I try to solve for X. But this one's going to be tough to find X. So it'd give you a very complex answer for X. So what do? I assume it's very small. Okay? And if it's very small, I can get rid of this term right here. Notice you may be saying, hey, if X is small, why don't I just replace this with 0? Well, then I would get that this equals 0. And I couldn't solve for X, and it'd be annoying, right? So I don't do that, right? So I make this assumption, plug it back in, solve for X, right? And then I go ahead and plug those back in to figure out my concentration. Okay? All right, now, what do I do next? I check my work, right, to make sure that I got a value for X or for K that is close to what I started with. Okay. All right, now, I want to go back to one thing, and that's the assumption. Okay? So what I need to do is I need to check that assumption. Okay? And I'm going to use something called the 5% rule. The 5% rule says that assumption is good as long as it results in less than 5% error. Right? So if I tell you I'm going to give you $100 and I end up only giving you $100 or $98, you say, that's 2% off. I'm not going to bother. All right? Let's do that with this. Okay? So I assumed that 0.824 minus 2x equals 0.824. Right? In reality, I found out that it was 0.81. So what do? I take this number, right? So I take, this is the percent off, equals actual, or the assumption minus the actual over the actual. And I just do it so that it's always positive, so I do absolute value. What these signs, if you don't remember, is I do this and I just make it positive. And then I multiply by 100%. Okay? All right, so I'm going to take my assumption, which was 0.824. Let's go. Minus this value, because this is what it actually ended up being, over 0.81. I take that, multiply by 100%, and I go ahead and I find out that this is 1.8%. So this is a good assumption. It's less than 5%. Okay. On the board, you can see it again. I went ahead, I did assumption minus actual over actual, and I made sure it was less than 5%. Okay. So that is a simple way to do an ICE chart. And it's when we can assume X is small. I can assume X is small if Q is very close to K, right? Because remember, X is my value, right? So let's say here's my Q, here's my K, here's my K. I already said, hey, I always shift either left in this case. If I want to go to this K, if I want to form the red K, it shifts towards the right. Okay? But if Q and K are very close, like they are here, that means it's a small shift. So I can use the assumption. If I had this where my Q is here and my K is far away, in this is a large shift. So I have to use something called the quadratic equation, which we'll do next time. All right. How do I know if X is small? Well, there are no rules. If you look it up online, they'll tell you about the 100 rule or the 1,000 rule. There are no rules. But we can say that typically we can use X, this assumption that X is small, if both Q and K are smaller than 0.01. Or if both Q and K are larger than 100. But if Q is greater than 0.101 and K is smaller, then that's a large shift. Or if Q is 2 and K is 3, that's a large shift. Okay? So they both either have to be greater than 100 or less than 0.01. All right, let's go on and let's look at video problem 15A. You're going to do this yourself, see what you get. Now I'll give you one, and don't worry, if you need to watch the video, go ahead, watch the video, pause it, do the next step, then pause it. Try to do as much as possible. We'll do more ICE problems next time. It takes some getting used to. All right, so in this case, we have NH3 plus H2O goes to form NH4 plus OH minus, right? I'm going to tell you, you can use the approximation here, but I want you to prove that that's okay by looking at the 5% rule and by checking your work by looking at K. There's one other thing you should notice here. Notice that H2O is a liquid. So what that means is it's not in your calculation for Q or for K. So what does this mean? When you set up your ICE chart, you're going to have NH3 plus H2O goes to NH4 plus and OH minus. You're going to not have anything in the H2O. You're just going to have, oops, that was a bad. You're just going to have values for your NH3, your NH4 plus, and for your OH minus. Okay? You're not going to include anything for your H2O. All right, but go ahead, do this, see how you get. We'll work through it. Come to office hours, come to SI if you need help. All right, next time we'll look at harder ones. We'll go use the quadratic equation, this one right down here, and then we're going to look at some other cases. All right, here are some videos. These two are this one on quadratic. You'll figure out next time. But here's one using assumption. Here's one using ICE tables. Go ahead, look at those. If you need someone else who explains it another way, that's fine, right? Also, SI. This is another way. Talk to Nimrod. Try to figure it out. Try to get another voice to try to help you out. All right, so that is it for equilibrium calculations number 1. Next time, we'll talk about some harder problems. All right, talk to you later. Bye.